speaker is Amanda Peiffer from Denison University, and she'll be speaking about knot mosaics. What is your number?
Hello, again, I'm Amanda, and I'm from Denison University, and this summer I focused on knot theory in the mathematics department. So to begin, I just want to go through what we're going to talk about. So we're going to first define what a mathematical knot actually is, then we're going to talk about crossing number and right-of-ways removes, and last we're going to talk about mosaic number and building these knot mosaics. So to begin, what is a mathematical knot? When you think of a knot, this is like the image that typically comes to your mind. But this actually isn't a mathematical knot because mathematical knots can't have ends to tie or untie. So instead what you would need to do is just connect it like this. So here's a picture of different knots, and these are classified by their crossing number. And the crossing number is basically the minimum amount of crossings you can get for these knots. So for instance, the unknot is just a circle. You can't get less than 0 crossings. And then 3-1 has 3 crossings. No matter what you do to this knot, you'll never get it to have less than 3 crossings. As you can see, the more crossings you add, the more unique knots you get. The interesting thing is, you can always add more crossings to knots. So you have these things called right-of-ways removes. So assuming that this strand is part of a knot, you can always add a twist to a knot, which will add a crossing. And we'll see this a lot. So this is a right-of-ways type 1 move. Additionally, you can take 2 strands of a knot and overlap them. Again, none of these are going to actually change the fundamental properties of these knots. Lastly, this one's a little bit harder to visualize, but you're assuming all these 3 strings are coming from one knot, and you're just basically sliding one over another. So these are your 3 types of right-of-ways moves that you can use to transform these knots. So why do we even care about knot theory and knot mosaics and whatnot? Well, in the 1800s, scientists thought that knots actually correlated to the elements. And if you go back to our original picture, it kind of looks like the foundation of our periodic table of elements. So they thought these knots might be what are our elements, and obviously that's not true. But nonetheless, what has happened since then is scientists have actually taken this and used it in different fields. So for instance, I'm also a chem person, so this is awesome. So in chemistry, in 1961, these 2 scientists were able to get molecules to basically create this link, which is a really interesting thing. Additionally, in 1993, there was a group of scientists that were able to get 80 atoms to make this trefoil, which is the simplest knot. And then in 2007, there was another group of people at Franklin Marshall that were able to use make that same trefoil, but with only 63 atoms. So they're trying to see what's the least amount of atoms we can get to make this knot, because it'll completely change the properties of the molecule, which is really interesting. Okay, so going into knot mosaics, which is what I looked at this summer. So in 2008, Lamonaco and Kaufman were 2 mathematicians who developed this idea that we're going to take knots and basically project them into a 2D representation. And they defined these 11 tiles as T0 through T10. And with these, you can build any knot. Following this, the mosaic number is basically the smallest board you can get the knot onto. And these are square boards. So if we're looking at our trefoil again, we know it has 3 crossings. So our question is, can we get this onto a smaller board? So right now it's on a 4x4. Can we get it onto a 3x3? Well, if you look at this, there's only 1 inner tile, and you can only put crossing tiles on the inside because if you put it on the outside, it's connecting to nothing. So we know that its mosaic number has to be 4. Additionally, the next knot would be 4-1, and we know that this has 4 crossings, and right now we got it to fit on a 5x5. But can we get it to fit on a 4x4? So if you look at the 4x4 that the trefoil's on, if this has 4 crossings, we're going to have to pack the whole inside with crossings. Well then if you do that and you fill it up, you end up getting this link, which isn't our knot, so we know that that can't be right. Additionally, if you end up connecting it the other way, you get those right-of-ways type 1 moves, those twists. And if you can see, you just untwist all 4 of those and you get a circle. So that's not right either. So because we tested everything, we can conclude that the mosaic number of this is actually 5. So looking at our chart again, we know that the unknot can fit on a 2x2 because it has no crossings. Additionally, we've shown 3-1 and 4-1. The 5 knots, the 5 crossing knots, were able to be fit on 5x5 boards. And since they have 5 crossings, they can't fit on 4x4s, So we know that those are their mosaic numbers. 6-1 was interesting because when it's fitting on a 6x6 board, it looks like this. But if you can kind of see, you can take this strand and flip it down. And when you do that, you actually condense it to a 5x5, but you increase its crossing number, which is kind of counterintuitive. That when its mosaic number is realized, which is on a 5x5 board, it has 7 crossings and not 6. 6-2, we were able to just place on a 5x5. Not quite as exciting. But mosaic number was 5. So then the one I looked at this summer was 6-3. And 6-3 we know has 6 crossings. So how do we get this onto a mosaic? Well, we were able to get it on a 6x6, but our question was, can we get it to fit on a 5x5 like the other 6 crossing knots? So looking at a 5x5, the inside has 9 potential crossing tile placements. So what we decided is we're going to use something called the pigeonhole principle, which many of you probably know about. So the pigeonhole principle basically says we have 10 pigeons, we have 9 boxes for them, so at least one box will have at least 2 pigeons. So it was interesting that we could actually use this for this research. So we have, there's our inner board, we're going to use the same idea. So we have 6 crossing tiles to place, and we have 5 non-corner tiles to put crossings. So at least one corner will have a crossing tile. And again, this is our inner board. So going back to that, we were able to use this to break it down into 4 different cases. So case 1, simple as we're going to put 1 crossing tile there. So we're not going to put them in the other 3 corners. We have 5 placements left. And then if you could see, you could rotate this 4 different ways. You end up getting 4 different arrangements. Case 2, we're going to put 2 corners. You can't put 3 crossings in a row on an odd board, because if you do, again, you get this Reidemeister type 1 move. So that means that the crossing number would be reduced, and at most this would have 5 crossings. So with that being said, we have 4 placements left, 4 tiles. We place those, and we get 4 different arrangements if you turn this 4 times. Case 2, we also needed to check the diagonals. When you do that, now you have 5 options and 4 tiles, which is just 5 choose 4, which gives you 5 different ways to place these. By rotation, this one only has 2 different arrangements because this only rotates twice. So you have a total of 10 arrangements for this one. Case 3, we have 3 corners having crossing tiles, 3 placements left and 3 tiles. So if we place those, again by rotation, we'll get 4 different arrangements. And then for case 4, all 4 corners. Again, you can't have 3 in a row, and when you do this, you only have 1 place left. We still have 2 tiles, so we don't get any arrangements from this. So we have a total of 22 different boards to basically look at. So when we did this, we constructed all of these, and from these, with case 1, the only thing we really got from it was the knot 6-2. And we already knew this fit on a 5x5, and we're looking for 6-3, so that didn't matter. Case 2, we got stuff that had all those twists again, those Reidemeister type 1 moves, so again, didn't have the right crossing number. Again, we got 6-2, and then we got a composition of 2 trefoils, which basically means just gluing them together. So none of these are what we wanted. Case 3, again, you get those Reidemeister type 1 twists, not what we wanted. In case 4, we didn't even have to check. So basically, we were able to conclude that 6-3 cannot fit on a 5x5 with 6 crossings. But then our question was, can we do it with 7 crossings? Because remember, that 6-1 knot was able to fit on a board when you added a crossing. So when you do this, you look at your inner board again. And we said we can't have 3 crossings in a row. So if you already say that, the most amount of crossings you can place is 7, which is what we're looking for. Well, each crossing, or each placement has 2 tile options, which are those 2. It's like the over and the under crossing. So basically, you have 2 to the 7th, or 128 different mosaics. So we built all of those. And when we did that, 122 were obviously not 6 crossings. And these go back to the Reidemeister moves, because as you can see, you can just take this top part and pull it down and pull that string. You lose 2 crossings, at most 5 crossings. 4 of them were the knot 6-1. Again, we already knew this wasn't interesting. And 2 of them were the knot 7-4. So none of them were the knot 6-3. So we were able to conclude that the mosaic number of 6-3 was actually 6. Thank you.
Okay, questions?
You obviously had to go through it very quickly, and it was a whole summer's worth of work. I'm just curious about the methodology that you used. did you, was this a matter of, like, when you talked about the 128 different possibilities right at the end?
Yeah.
Was it a matter of writing each one of those down and
Yeah.
staring at it and thinking about it, or is there an algorithmic way once
Of
you?
constructing them,
Well,
or after we got them constructed?
after you've constructed it,
So-
then analyzing it.
It was actually as simple as literally I just made all 128,
Yeah.
printed them out, and it was honestly as simple as just being like, this could be reduced by 2 crossings easily. So it was just crossing them out. So there were really only 6 of the
Yeah.
128 that I had to check.
So the methodology was your brain power. I mean, once you looked at it, then you could see
Yeah.
simplifications.
Yeah, we're using a lot of computer programming to do different stuff with the mosaics and with the crossing numbers and whatnot, but that was not something that the computer could do, or that we figured out how to quite do it yet, so.
How much did you use not jokes this summer?
A lot. Pretty often. Yeah.
Any other questions?
So you said something about you can't have like 3 in a row.
Mhm.
Was that just like on like including corners? You could have 3 in a row.
That's just the outer perimeter of the inner board on an odd size board. So there's a lot of like rules with it, but yeah, and that's because if you did that, you get those twists, which means that your board isn't as reduced as it could be. If that kind of makes sense.
Any other questions? Okay, thank you, Amanda.